Hello there. So today we're going to be going through this problem here. So it first says, 200 students are randomly sampled and asked two questions. What is your blood type? And do you play a musical instrument? The data is summarized in the table given. So the question we want to ask with this data is the probability of having blood type A independent of playing a musical instrument. Now we're asking this question so that we can explain the idea of independence among data, and this is a pretty good way to do it. Now there are a couple different definitions of independence, but here I'm going to give you a couple formulas that represent the idea of independence. And there are actually three. So the three are A and B. And I'll explain what the A and B represents in a moment. All right, so those are the three formulaic definitions of independence. So what does this mean? Well, first of all, the A and B just represents two different random variables. So here, we could say that A represents the random variable of having blood type A, and B being the random variable of the student playing an instrument. Now A can be blood type A, or it could be something else. It could be O, it could be B, it could be AB. So those are the different blood types it can be. But here we're gonna have A representing the random variable that the student has blood type A, and that has a certain probability. And B is going to represent if the student plays an instrument or if they do not. So here, the first, well, let's go to the second definition first. So that says probability of A given B is equal to probability of A. So what this means is the given part represents, let's say we know that B is true, that the student does play an instrument. So that means we would be only working with the data in this first column here, the play column, because we are told that probability of A given B, so the probability, we would like to figure out if the probability of the student having blood type A is independent of if they play an instrument. And if the probability of them being blood type A, given that they play an instrument, is equal to the probability of them being blood type A, then that means the fact that we were told that the person plays an instrument does not have an effect on the person being of blood type A. Explain that again with this part here, probability of B given A is equal to probability of B. That means that if the two types of questions, like if the student's blood type is independent of playing an instrument, then given that we are told that the student has a blood type A, then that will not affect the probability of them playing an instrument, because that would mean, as stated here, independence means that if given that we're told this additional information, it doesn't change anything about the probability of B. So we can use these different definitions and to figure out independence. But there's also this other one here, using the idea of the multiplication rule. So that's saying the probability of A and B, so the probability of the student having blood type A and the student playing an instrument is equal to the probability of them having blood type A times the probability of them having of them being able to play an instrument. So those are the three different ways that you can think of independence in a formulaic kind of way. So we can solve these problems, and I'm gonna label this, let's label this, where's that little pen? So I'm gonna label this one number 1, number 2, and number 3. And I'm gonna go through each one and show you how you would use the three definitions to show if this is the case, if the person having blood type A is independent of them playing a musical instrument. So using the first one, so probably of A and B. So in order to figure this out, we want to all probabilities can be turned into a ratio. So this would equal the number of students who have blood type A and play a musical instrument. Divided by the number of students. So here we can figure this out just by looking at the table. So what we do is we look for one of our rows. So this is the row indicating those students who have blood type A. And we want to find the column indicating those students who play an instrument. So that would be this column. So the intersection there is this 20 right over here. So that 20 we can write over there. And the total number of students in the bottom right hand corner of the table is 200. And that reduces to 1/10. We don't need to go into decimals right now. Okay. So now that's the left-hand side of the independence equation. Now if we calculate the right-hand side, probability of A times probability of B, well, probability of A is the probability of the student having blood type A. Now in order to do that, we figure out the total number of students in our sample that have blood type A, which in this case is 50, over the total number of students. So this will give us 50 over 200 times the probability of B. And that probability of B is the probability of a student playing a musical instrument, which in this case is going to be the total number of students who play an instrument over the total number of students that there are. So that will be 80 over 200. Now we can do a little bit of simplification here. We can cancel out the zeros. So we have 5 over 20 times 8 over 20. And we can reduce this a little bit more. That 5 over 20 is 1 over 4 times 8 over 20, which gets us to 2 over 20, which is 1 over 10. Aha! So that means that the right-hand side is equal to 1 over 10, the left-hand side is equal to 1 over 10, and that satisfies the formulaic definition of independence. So therefore, the probability of a student having blood type A is independent of whether they play a musical instrument or not. Doesn't matter. And one point of note is these three formulas I wrote up here. If one of them holds, then all three holds, and that is a guarantee every single time. So if you're ever doing a problem and you want to do a little bit more practice, or to check your work, if you do, say, this one, and you want to check your work again, you can do this one. And if you find that they both agree, then then that's just an extra check on your work. So here, let's move everything up a little bit, just a little bit. Okay, so let's go. Let's change color. Let's go with red. So then I'm gonna do part 2 here of the formula. So I'm gonna go probably A given B. And what this means is the given part B means we're only going to worry about the column where the students do play a musical instrument. That would be this column. So we're looking at this column, and A given B, so that will be the number of students who have blood type A, given that they play a musical instrument. So that's going to be 20 over 80. There you go. You can cancel out a little bit more. Now it gets to 1/4. Now the right-hand side of number 2 is part of A. So just the probability of a student having blood type A. Now, how many students have blood type A? 50 out of 200 total. So in order to calculate that one, we do 50 over 200. Those cancel out. We're left with 5 over 20, which is 1/4. And there we go. And that agrees. So number 1 agreed. So number 1 worked, number 2 worked. Let's go with number 3, just to show all 3. Let's go with green this time. So probably of B given A. So we're only working with the row indicating those students who have a type A blood type. And we want to, and the number of students who play a musical instrument out of all students who are blood type A is 20. So this is going to be 20 over 50, which can reduce to 2 over 5. And the right side of that equation is probably B. So the probability of student selected plays a musical instrument. So we will be working with, these are the total number of students who play a musical instrument. That's 80 over 200. So it'll be 80 over 200. We can cancel out the zeros. We're left with 8 over 20. And we can divide the top and the bottom by 4 to get us 2 over 5. And that agrees too. So here we have shown that blood type of probability of blood type A is independent of any of the student playing a musical instrument in 3 different ways. Now, whenever you're doing a problem in the future, you can use any of these 3 ways. Depending on the information you're given, one way might be easier than the others, but all 3 will work if you can choose any of them. And that is how you show whether 2 random variables are independent or not.